So in the first part here, there's this chart. I've already told you the relationship between these, so I don't think we need to make the chart. The derivative, let's make sure my pen works. The derivative with respect to x of e to the x is e to the x. If we were to go make the table and write all these down, and then in y2 have it give us the derivatives, they will be the same. And I've already told you that in another section that they truly are the same. So that's going to be a derivative we're using. It's the only function in the world whose derivative is itself, and I'm going to prove it to you, not actually for its proof. I think I might have proved it already for you. Am I right? No? Well, we'll go take a look at it. Let's let y equal e to the x. So you can see why the derivative of it is itself. Anytime that you have the variable in the exponent like this, 9 times out of 10 you don't want it there, and we remove it by taking the natural log of both sides. Because if we can do that, then what I can do is pull this exponent out front, and I've got the natural log of y equals x ln e. I haven't taken a derivative yet, but I'm going to in just a little bit. Before I do that, I'm going to replace ln e with its numerical value, which is 1. So really what I've got here is that the natural log of y is equal to just x. Right now, I'll take the derivative. I'll take the derivative of the left with respect to x, and the derivative of the right with respect to x. And in this proof, what I would then have is on the right-hand side, let's move up over here. On the right-hand side, I'm going to have a 1, because that's what the derivative of x is. On the left-hand side, we have that the derivative of the natural log of any function is 1 over the function times the derivative of the function, which in this case would be y prime. So if I'm trying to figure out what the derivative is, I get y prime is equal to y. It's the function itself. It's the only function in the world where that happens, that its derivative is actually itself. It makes it really easy to work with. It's probably one of the easier derivatives in the section today. The worksheet is quite easy to get the answer. It's going to be getting the best answer. That's going to be the only problem. So just simplifying things. So also we have that the derivative of e to any function is e to that function times its derivative. So we're just going to go practice. They're going to go really quickly on this first page, and then I'll slow down a little bit. I might not write a whole lot on this page, but let's go take a look. So on the first one, I'm taking the derivative of e to the u. The derivative of e to the u is e to the u times u prime. So I end up with 5e to the 5x. It's as easy as that. Go to the next one. Same thing. It's 4e to the u. So its derivative is going to be 4e to the u times what? Negative 2. Yep. So that one, when you're all done, you're going to get a negative 8 e to the 1 minus 2x. And that's what your y prime is. We can skip this one. We'll go take a look at number 4. Number 4, constants don't affect anything because when I do the product rule and I do first d second plus second d first is 0, it wipes it out. So I really just have 2 times the derivative of this function, which would be e to the u times the derivative over at x, which we've had a zillion times, right? 1/2 x to the negative 1/2 or 1 over 2 root x, and those would cancel. Whoops, that's my y prime. So very easy. It says we now have 6 basic rules for derivatives, but I forgot one, and I have them listed on the next page, so let's see if we can see which one I forgot. We have the power rule that we use. We've got product. We've got quotient. We've got 6 trig rules for cosine, sine, tangent, cotangent, secant, cosecant. We've got natural log, and now we've got e. There's a big hitter missing right between these two. What is it? Chain. And that's one of the biggest ones. Yep, so let's put chain in here, and let's change that to 7. And now all you're going to do is use all the rules, including the e. So notice on all of these there's an e somewhere. And then we're going to ask some common questions. Let's go do number 5. Number 5 would be a clear case of chain rule combined with e. So all I would do is chain it first, and I'd say it's 2 times e to the x plus 3 to the first times the derivative of the guts, which I have now just told you is always, what's the derivative of e to the x plus 3? E to the x. So this is just going to be 2 e to the x times e to the x plus 3. It's very easy. Number 6 would be a clear case of the product rule. You could do it without showing any work. You would just do first d second, which is going to give you x e to the x, plus second d first. So you're just going to have x e to the x plus e to the x. Easy peasy. The next one, what rule would be applied first? What rule is it? Go ahead, tell me. It's okay that I'm on video. Go ahead and tell me. They can't hear you. Exactly. There's no one listening to it in Aaron, and he'd probably love to hear you. All right, so yeah, it's a clear case of the chain rule. So I am going to do cosine, and actually Kyle, and there are 2 other people gone for the rest of the week. We've got cosine e to the x times the derivative of e to the x. Usually we put our simplest function first. So that's how that one would look. It's nice and easy. You could do, let's just do number 8 in our head. It'd be e to the sine x times cosine x, and I'm done. Now on number 9, we're going to combine it with our, see, I'm going fast. I told you. Notes are, I'm going to try to keep it at 20 because I was told it would be over 20, and it won't be. All right, number 9, natural log of u, its derivative would just be 1 over u times the derivative of u. And the derivative of u would be 1 plus e to the x. So I can almost just go tweak it and not have any work whatsoever. It's nice. I'm not going to do number 10. But I want to go do number 11 and talk about making sure we clean things all the way up. So this is a clear case of quotient rule, which we should have memorized. Let's go crank it off here. We have low, d high, minus high, d low. What's wrong with that? Purposely made a mistake. Low d high minus high d low. I forgot the 4 on purpose, just to make sure you're watching me. So low d high minus high d low, draw a line and square below. This will not be what you'll see on my answer key, because I do have all the answers on Edmodo. I don't have the work, and that's what last hour they're coming up, and they'd say, what did I do wrong? And I said, nothing. It's just could get a little better. So if I were to factor the top of this, sometimes factoring doesn't make things better. So it's not necessarily necessary, but on this one, factoring would make it better. Why? Because of the canceling. So usually if factoring doesn't cause canceling, a lot of times it won't. We just won't factor it. But when factoring is going to cause canceling, so that when I cancel this off, I just end up with an e to the 4x on the bottom. That is much better. If factoring causes canceling, do it. That's kind of the motto. We can skip number 12. And we're going to go right on to the next page, and we'll do these 3 and be done. So here's 3 skills we're already really good at. We know how to do implicit. We can take second derivatives, and we also know how to find relative extrema and inflection points. The only thing different on here is that embedded in all this is e, which we haven't had before, but we won't change our process. So with implicit, we're going to take the derivative of the left-hand side with respect to x. So I'm just going to rewrite this. The derivative of 0 is 0 with respect to anything. So there's no rate of no change if there's nothing to change. Anyway, one of the biggest things College Board does when they give you implicit is they always give that. They always put one where there's product rule, because most kids do this. They'll go like this. First, d second, which would be e to the y, but then times what? Y prime, and then they go plus 8 minus, they forget the other part of it. And then you'll see your answer always. So make sure when you're doing implicit and you do first, d second, don't forget second, d first. That's really common to leave this out. The derivative of 8x with respect to x is 8, and 3y is 3y prime. Our implicit process, we isolate y prime, so I'm going to get all the non y prime terms over to the other side. So just do a little rewrite here. I'm purposely going to take this one to the end to discuss how to write your final answer. So now that I've got y prime all on the left, I factor it out. And I get x e to the y minus 3, right? Did I do something wrong? Am I good? All right. And I've got mine. I just heard somebody. All right, there we go. And then at the end, to isolate the y prime, I'm going to divide. So just because I'm too lazy to write it, I'm just going to cross it off and go stick it on the bottom over here. Now, general math procedure is to use as few negatives as possible. So that's generally not how you would see this answer because I've got lots of negatives going. So what will usually happen is the opposite of the top will be taken, and it'll be 8 plus e to the y or e to the y plus 8. Usually the function comes first and then the constant. So that's probably what you would see on the top. But if you take the opposite of the top, you're kind of basically multiplying it through by -1. You also need to do that on the bottom. So this would either be negative x e to the y plus 3, or usually if there's subtraction, they put the positive one first. It's just kind of making it pretty. So these are the exact same answer, but the blue one is considered prettier. And it actually truly is prettier, I think, right? It's lovely. So now we already know how to take first and second derivatives. We've just never done it with e before. And we've never had this bottom question with e. So let's go take our first derivative. The derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times -1, which is going to put a plus there. So when we're down here looking for our relative extrema, we are going to be working with this first derivative because that's what relative extrema involves. So I'm just going to launch that down below. It's the same function right here that we're working with. My second derivative will be the derivative of my first derivative, which is e to the x, and then e to the negative x times -1. It goes right back to being the original function. So over here, my y double, I just don't want to have to reinvent the wheel since I'm using the same function. So here's my questions, and then I'm done. This is the last one, and I'm only at less than 13 minutes. I was challenged. Somebody asked me how long it was going to take, and I said less than 20. And he said, you always say that, but then you're over. So I'm making up for overused time today. Look at that. Maybe I'll just stand here and chat until it gets to 20. No, I won't. All right, so back here, we are doing relative extrema. We've had this question a lot. It involves the first derivative. It isn't where the first derivative is 0. It's where the first derivative changes sign, but when you can't see it, you have to find where it's 0 first. So what I first need to do is figure out, is there anywhere where the first derivative, which is really this, I always like to get, when I'm working with numerical values, I like to get my negative exponents out of there. I also, technically, if I use common sense, could answer the question right now, but usually in the process of higher level math, common sense leaves people. But I would challenge you that there's no way that could ever be 0. Can you see why with common sense? Think of the graph of e to the x. It's always positive, correct? And 1 over e to the x will also always be positive. Can you do a positive plus a positive and get a 0? So common sense tells me that can't be 0, which means there's no way there's any relative extrema because this is positive everywhere. First of all, also, if you know the first derivative is positive everywhere, we know the original function must be doing what everywhere? Increasing. That's actually got a name. It's called a monotonic function. You don't need to know that, but this is actually what we call a strictly monotonic function. It is increasing everywhere. But let's suppose you didn't use common sense and you used some algebra. You usually like a common denominator, and you'd say e to the 2x plus 1 over e to the x. For a fraction to be 0, the numerator has to be 0, and there's no way that you can have a function that's squared, because that's really e to the x squared, always positive, right? Plus 1, still positive. That can't happen. So there are no relative extrema. Why? prime can never equal 0 for any x value. So no rel extrema. First, and also if I really get it, I know that the function is what we call strictly increasing. It's called monotonicity. Huh! Love that word. That's a good word. I think I made it up, but I like it. It's actually called monotonic, but we're going to say it. All right, so the second one, just because it's always increasing, you can't say, well, that means there's no inflection points. That's not true. Functions can change concavity without changing from increasing to decreasing. Could you picture what it might look like? If it's always going up or always going down, but there is a concavity change, what might it look like? Oh, interesting. Yes, that's a good one. We'll see what this one looks like when we go graph it when we're done. This actually does have an inflection point. Let's go find where it is. An inflection point occurs when the second derivative changes sign. Well, I can't figure that out until I figure out where it's 0, so I'm starting this the same way. It is possible for this to be 0. You could either use common sense and see it, or you take some math and you do crisscross. So e to the 2x minus 1 over e to the x. It is very possible for this to be 0. And you could use common sense again. What could x be so that I could get a 0 out of that numerator? Just common sense, no math whatsoever. 0. That would do it, because e to the 0 is 1, 1 minus 1 is 0. But suppose I didn't use common sense, and I was truly going to use some algebra to figure out when, whoops, sorry, I'll put my minus up in the exponent. Suppose I was going to just kind of be a rule follower and not use common sense. I would take the numerator, set it equal to 0. I would want e to the 2x to equal 1. Common sense maybe should kick in right there and say the only way I can get a 1 is if the exponent is 0, but let's suppose common sense fails again. How do we get this out of the exponent? Just supposing common sense left you for a day. ln. You could then analytically just manipulate this. ln 1 is 0. 2x ln e is 2x times 1. Now definitively, without common sense, what's x? 0. All right. Does that mean, by the way, that I have an inflection point right here? It's what I call a pip. But I don't want a pip, I want an ip. What's a pip? Possible inflection point. It's possible, but it's also possible it's not. Here's a perfect example of a function whose second derivative is 0, and there is no concavity change. Y equals x to the 4th. I'm going off on a little tangent here. Pardon the pun. Ha! Look at the time. I'm going to be right on. This is great. I have just enough time to go off on a tangent. Are you ready? X to the 4th actually looks like a quadratic, but it flattens a little bit down here. First derivative, 4x cubed. Second derivative, 12x squared, correct? Which is 0 at 0. All right, but my second derivative of 12x squared is positive everywhere, and that's concave up everywhere. So there's an example where a pip of 0 is not an ip, right? But my pip over here, how do I check to see if it's truly an ip? I run a check. I will check to the right, and I'll get a positive. I'm not going to go do it because I want to be true to my promise. I've got 1 minute. And I'll talk really slowly to get it to 20 minutes because I promised a 20-minute lecture. This is what will happen. Therefore, we have got an inflection point right here. Now, my last minute, less than that I'm offered, I want to go graph that. Somebody take out their calculator so we can confirm that truly we've got an original function that had no rel extrema. Oh, really slowly. Thank you. We've got a graph of the original function. It went like that. It looks very cubic-y, but it's not. It's e to the x minus e to the negative x. And you'll notice there is no change in the derivative. It's up everywhere, but there is a concavity change right there. It went from concave down and then switched to concave up. Fantastic. And I've got 10 seconds to sing. What should I sing? Huh? I'm too sexy for my shirt.